All right, so now let's kind of review what's going on here. What we just did in 11.9 is we found a way to represent certain functions as power series, right? That's the whole point of what we just did in 11.9. And to do that, we were using heavily using the geometric power series, right? What if we have functions where there's no way that we can ever write it as anywhere near the 1 over 1 plus x or something like that, right? And of course, there's plenty of functions like that. But there's no way you're going to be able to write it as like some form of 1 over 1 plus x or 1 over 1 minus x, no matter how many derivatives you take, no matter how many antiderivatives you take, it's never going to happen, right? Well, such as sine and cosine, right? You can take as many derivatives as you want. You're never going to get a function that looks like 1 over 1 plus x, 1 over 1 minus x. So what do we do about those functions? How do we find the power series expansions for those? And so for these, we use this cool thing called the Taylor series. The Taylor series. So this 11.10 is kind of putting all this stuff about power series together. It starts out by saying what is the form of a convergent power series. This is a little bit of a review here, but it is putting it all together. If I want to make a power series for a function, however I do it, what is it going to look like at the end of the process that I use to get there? It's going to look something like this. I'm going to have some coefficients. I'm going to have x minus the center raised to some power, and it's going to converge on some interval around a, whatever a happens to be. Okay, that could end up including the endpoints as well. So anyway, that's what any power series is going to look like, regardless of how you get to it. Now the coefficients here, that Cn is going to be equal to the nth derivative of a divided by n factorial. How the heck does that happen? Let me just kind of go through the thinking about this. So our goal here first is how do we find a power series representation for any function? That's the goal here. How to find a power series representation for any function. And what we're going to do is first start out by approximating a function with a polynomial. And what we're going to find is that once we figure out how to approximate it, then we can actually take that directly to equality, not just approximately equal to, but exactly equal to. How do you approximate a function with a polynomial? So I'm going to go through this process of how we think about this, and then what we'll find is it actually does generate the formula that we see there for what's called a Taylor series. So I'm going to do this centered around 0, but this can certainly be expanded to be centered anywhere. So everything that I'm going to say here can be extended to any center. It doesn't have to be 0. Okay, so the goal here is we would like to say some function f of x is approximately equal to some polynomial function. Now there's a couple things there's a couple of caveats we have to place on that function f. It has to be differentiable infinitely often, so you can't do this with functions that aren't differentiable infinitely often. But most of the functions we're dealing with are, so like sine and cosine, tangent, all that stuff are. So those are good. So again, the goal here is we're trying to approximate a function f of x with this polynomial function. And what I'm saying here is that this n here, the p stands for polynomial. This n is the degree of the polynomial. So what I'm saying here is we want to approximate this function with an nth degree polynomial, nth degree polynomial, okay? How do we do that, and what's the thinking behind that? Well, if you think about it, if I want to approximate a function with another function, there's a few things that maybe we should say need to be true. For example, the outputs of the function should be the same. And let me actually just go ahead and write what that nth degree polynomial is going to look like. What does an nth degree polynomial look like? It has some coefficient. It's got x to the nth power, right? That's an nth degree polynomial. And then it's got some other coefficient. And then we've got one power lower than that, and then a coefficient associated with that lower power. And then we've got a coefficient that's associated with the one that's 2 less than that, and so on. Right? And so this just keeps going until we reach like the second term, and then eventually down to the first term, right? And I guess if you want to call this the 0th term, you can, right? Because there could be a constant on there. All right, so that's just what I've written there is just any general nth degree polynomial. And so remember that polynomials are completely determined by their coefficients. So if we can determine what these coefficients are, all of these coefficients, every single one of them, if we can identify what all those coefficients need to be, then we will have a formula that approximates the function fn. And so our goal is, again, to figure out what those coefficients need to be. Maybe we can find a formula for them. All right, so how do we do that? Well, again, like I was saying before, there's a few things that if you want a function to be approximated by another function, well, what should happen, right? Well, a good approximation would have the same output value, right? Or at least pretty close to the same output value when you plug something into the function and then you plug something into the approximating polynomial, right? So in other words, what we would like to see is that f, and since we're doing this at 0, we're going to say that it's going to be exact right at 0, but then maybe a little bit further away, maybe it's not going to be so great. But at the center, it's going to approximate it exactly. In other words, we want f of 0 to be exactly the same as Pn of 0. At least one of the things that we want. Well, what's Pn of 0? So if you look at it, what is Pn of 0? If I plug in 0 for this polynomial here, that means all of these are going to be 0, right? All the x's are going to be 0, but that isn't, right? So since it doesn't have an x with it. So what is Pn of 0? It's the constant term. It's c naught. So that means that we've identified our first coefficient. The first coefficient for this approximating polynomial should be whatever you get when you plug in 0 to the function. Okay, so like if this was the sine function, for example, if I plug in 0 to the sine function, what do I get? I get 0, right? And so that's telling me that my first coefficient should be 0. If it was a cosine function, then I plug in 0, I should get 1, so the first coefficient should be 1. Whatever I get when I plug in 0 should be the first coefficient, the c naught coefficient. All right, so what else? What else would we like to see happen? Well, again, the goal is to take a function, any function, and approximate it with a polynomial. Well, again, we're doing this at 0, so what else should we want to have happen at 0? Well, we would probably want the approximating function to have the same slope as the original function, right? And so that means we would like the derivative at 0 to be equal to the derivative of the polynomial at 0. Okay? Well, to do that, let's take a look and see what that derivative actually is. Okay, and so in fact, I'm going to kind of do this off to the side here. What is Pn or P prime of 0? Well, to find P prime of 0, I probably want to find P prime of x. So let's see what P prime of x is. Well, that just means taking the derivative of this polynomial, right? So how do I take the derivative of a polynomial? I just use the power rule, right? So what's the derivative of this function? It's going to be n Cn x to the n minus 1 is the first term, right? Plus n minus 1 c sub n minus 1 x to the n minus 2, and so on and so on. C1 is what we're going to eventually get out of this. So if I do this, and all of those terms, the powers are all going to go down by 1. As we get to these last few terms here, I'm going to reach first power there, then I'm going to get C1, and then the C naught term is gone, right? Because I took the derivative, that term's gone. This derivative is that, right? C1. And that's the only term that's going to be left when I plug in 0 there, right? And so what is Pn prime of 0? It's C1, okay? And so that means I should have a C1 there. Okay, and then just you can kind of maybe see where this is going. What else would we like to see? Well, we would like to see the second derivative of the function be the same as the second derivative of the polynomial function. So we would also like to see f double prime be equal to p double prime. Okay, and then again, we would maybe want to think about what that p double prime is. And so again, we just use the power rule again, and that means that n minus 1 is going to come down front. So we're going to get n minus 1, c sub n, x to the n minus 2. And then this keeps going, right? We'll have n minus 1, we'll have n minus 2. These terms don't really matter too much. It's the ones on the end that we really care about. And then we keep going, da da da. And then the last one, we're going to get 2c2, right? And then this one is gone now because we took the derivative, right? And that's a constant. But the derivative of this, the x goes away and you get that. You see? And so what is Pn double prime of 0? It is 2 C2. Okay, so this is 2C2. And this is telling us then, what does C2 have to be? We want to find what the coefficient is, right? So C2 is actually going to be equal to F double prime of 0 divided by 2, right? So what I'm doing is saying, well, I got to get rid of that 2 there. I'm going to divide that by 2 also. I'm solving this for C2, in other words. That's the goal here. And I think one or two more, and you can maybe start to see what the pattern is here. So what else do I want? I would like to have the third derivatives be the same, right? The third derivative should be the same as well. So what's the third derivative? Well, again, what's the third derivative of this polynomial? Again, these terms don't really matter so much. In fact, I think I'm going to skip some of them. I'm just going to skip all the way to the end there. That's the first term, then we got all those other ones. Well, what's the next one? Probably should have put more of these. Yeah, suppose I would have had the third power on here, right? Like C3 x to the third. Then I would have had right here 3 times 2 C3 x squared, right? And then if I put it right here, I would have had 6 C3 x, right? And then finally 6 C3 would have been right, what's right there, okay? And what is that 6, right? That's 3 times 2, right? Or in other words, if you want to say that's actually 3 factorial is what that is. And so what we're going to get here is 6 C3. And so that's telling us then that C3 must be equal to the third derivative at 0 divided by 6. All right, then if you can kind of follow the pattern here, we would like to see the nth derivative. You know, if you just follow what I was doing there on the right, what's the pattern? Well, I'm probably going to get, notice that I'm on the third derivative here, and I got this 3 factorial right there, right? And if you continue that, you would have seen a 4 factorial in the next one, and so on. And so we would have seen the nth derivative at 0 would be equal to n factorial times c sub n. And that would finally allow us to say that the general formula for the nth coefficient on this must be the nth derivative at 0 divided by n factorial. Okay? And again, what this is telling us, this is a general formula now that's going to tell us what every single one of those coefficients has to be, up to the nth one. And this is called the Taylor polynomial, this thing here. It's called the Taylor polynomial. You guys might have heard of the term Taylor series before. And then you can kind of see the way, so what we have here is a formula to tell us what that nth derivative is. And so the Taylor polynomial, nth degree Taylor polynomial, is this. Okay, so then you can kind of see the way that's defined. They say T for Taylor, and then the nth, the n down there means we're talking about the nth one. And you can see the formula there, and I'll write this out longhand so you can see that it matches what we just did. That is a typo. That should be starting at 0, not 1. Okay, now the one that I did was centered at 0, meaning it just had an x there, but you could do exactly the same thing if it was centered at a, and so that's why we're getting this one that's centered at a here. It's more general. Okay, now if you look at what this actually is, if you write out the terms here, look what you get. Like, what's the first term here? You get f0, the 0th derivative of the function. What's the 0th derivative of a, oops, that should be a factorial there. 0th derivative of a function is just the function itself. Okay, so basically, you're just going to get f of a there. X minus a to the 0 power is just 1, so there's that. And then the next term you're going to get, so first derivative of f prime divided by 1 factorial, so that's just 1. You get f prime of a, and then x minus a to the first power, and then you're going to get f double prime over 2. Notice that's 2 factorial there. You get x minus a to the second power, and so on, right? So that what I'm doing is just writing this out. And the third one would be the third derivative at a divided by 3 factorial, which is 6. And then you have an x minus a to the third power. And in general, the general derivative that you're going to have there, the last one, is this one. You're going to have the fn, nth derivative, evaluated at a, divided by n factorial, times x minus a, the nth power. Okay? So there's that same formula that we just derived, fn of, we had it at 0 again, but then there's the n factorial in the denominator. And remember that we were just trying to find the coefficients, right? Like if you come back up to the top here, we were just trying to find what these coefficients are, right? These things were just there. All of that's just there. So anyway, this is the approximating polynomial. This is the Taylor polynomial formula, okay? In fact, I think this might actually be a good time to just show kind of what this does. Let me jump down here to the Taylor polynomial for sine x, for example here. And I've scrolled down to the end of 11.10 here. There's a thing that says power series for elementary functions. You can kind of see where this is coming from. Now, this is actually, somebody's already plugged all this stuff into the formula here for us. In fact, actually, let's go ahead and just do this so you can kind of see how this works. Let's just do it with sine x and see how this actually works. Let's say centered at 0. So just notice this would be the way that you would think about this, okay? I'm trying to figure out a formula for the sine function. And so think about if f of x is sine x, then f prime of x is cosine x, right? And the second derivative is negative sine x. The third derivative is negative cosine x, right? And then just thinking about what all these are when you plug in actual numbers, right? When you plug in 0. What is f of 0? F of 0 is 0. What is f prime of 0? It's 1. What is f double prime of 0? It's negative 1. I'm sorry, it's 0 again, sorry. And then what is the third derivative at 0? It's negative 1. So these are the coefficients, okay? And if you think about, what the formula that we just got here, look at what this formula up here is going to produce, right? If I think about what we got here, what is f of 0? It's 0, right? So I get 0 plus, then the next term is this one, f prime, which is 1. So I'd have a 1 there. I just have an x. Then the third one is just 0, so I get plus another 0. Then I'd have minus what? 1/6, and then I'd have x to the third on that, okay? And then we could keep going like this. But if you see, somebody has figured this out for us. If you look at that table that I was talking about there, look at what you have for your formula here. You get x minus x to the third over 3 factorial, right? And again, I'm just looking at that table. It's at the end of 11.10. Well, look, that's exactly what this is, right? And so, like I said, this has already been done for us. And we know that the next one's going to be 5th power, and then a 5 factorial, and so on and so on. And then we can get a general formula for that. And they do that for us, in fact. So this is plus dot, dot, dot. And the general formula there for the nth term of this is this. And you can see that this formula is going to actually match what we have. So in fact, in this case, I'm going to have to put an approximately equal to because this is just the nth approximating polynomial here. Now let me show you something on Desmos about what we've just done. Okay, so I'm going to share Desmos now. Okay, so we got as our Taylor polynomial 0 to, let's do, again, I'm just going to do a there, and we'll do a slider so we can see what happens on that. So I'm going to put in the formula, so we'll have fraction negative 1 to the n, x to the 2n plus 1, over, what do we have in the denominator there, 2n plus 1 factorial. Let's add a slider for a. We'll start it at 0. We'll go up to 50, I guess, to see, step by 1. Okay, and then just also let's go ahead and add in the sine function itself. So y equals sine x. All right, so now, again, this is an approximating polynomial, right? Approximating polynomial. So this polynomial that I have here, right now, when I have a equal to 1, well, look where the a is, right? There it is. If a is 1, what degree polynomial do I actually have here? Third degree, right? Is that a third degree polynomial? Well, look at the red line there. You see? It looks like a third degree polynomial, right? It kind of comes from above, has its third degree behavior, and then goes down, right? So what if I increase the degree of the polynomial? I can just do that with the slider, right? If I make the a 2, then I've got myself a 5th degree polynomial there, right? It kind of looks like a 5th degree polynomial. And look what happens as I keep going up, right? 7th degree polynomial, 9th degree, 11th. Okay. So what are we doing here? We're getting exactly what we wanted, right? We wanted the output of the function to be equal to the output of the approximating polynomial. It is 0. And we wanted all the derivatives to be the same, right? All those derivatives being the same, the higher we make the degree of the polynomial, the further away that it actually matches the sine function. So what we're doing here is we've found a way to get the sine function without actually having to deal with the sine function itself, right? All we're doing here is just we're dealing with a polynomial rather than the sine function. You see that the higher I make this thing, the further away that it actually matches the sine function. Do you see how that's working? Once I get out to 50th degree polynomial, we're almost exactly matching the sine function way out to 35 or something away, 30 away. So now when we go back to let's go back to the worksheet. And if you just kind of look at the part where it says, now I'm back on 11.10, this is the approximating polynomial, right? This is approximately what the sine function would be. You can take it to any level of approximation you want by just increasing that n there. Okay, now what if we want exact equality though? What if we want this power series here to be the exact same thing as the sine, not just to approximate it? So for exact equality, what do? We just take the limit as n goes to infinity for this Taylor polynomial. And then that is actually going to be equal to the function. That's exact equality there. So again, if you come back up here to the Taylor polynomial that we were talking about, if I let this n right here, this is what I'm talking about, that n right there, if I let that go to infinity, then I get exact equality, and I get the formula then for the Taylor series, not just the Taylor polynomial, but the Taylor series. So when you have a Taylor series, that is just a special kind of power series, okay? And the Taylor series can be written like this. So there's that nth derivative. In this case, we're centering it at 0. And then, yeah, so that's exact equality there, okay? Not just approximately equal to. All right, so now, in fact, ones that are centered at 0, you might hear this term here. It's called the Maclaurin series instead of a Taylor series. All that means is that it's centered at 0. If it's centered anywhere else besides 0, it's called a Taylor series. Okay, but they're basically a Maclaurin series is simply a special case of a Taylor series. It's just the one that happens to be centered at 0. Centered anywhere else, you would call it a Taylor series. All right, so what is a Taylor series then? A Taylor series is a power series, just like those power series we've been talking about in section 11.9 and 11.8, right? Those are power series. This is also a power series. It's a power series that just happens to have a formula associated with it. There's your formula right there that tells you what those coefficients are for all the coefficients are, okay? Now, in the book, they also mention a little bit about this notion of a remainder. I mean, it is important. What we want to see here, yeah, how it says Taylor polynomial right there, the nth partial sum for the Taylor series at A is that. It's called the nth degree Taylor polynomial. So back to that Taylor series, if you have, or back to the Taylor polynomial, I mean, the one that does end, right? It starts at I equals 0 and it goes up only to n, stops at n. That's the one that I was trying to show you on the graph, the sine function. Ith derivative evaluated at a over I factorial. You can kind of see what they say there. With this, we saw that this doesn't match the function exactly, right? I put that up at about 50, and we saw that once we got pretty far away from the center, the polynomial started shooting off, right? And so there was a difference between what the polynomial outputs and what the function outputs, right? The sine function outputs something different than the polynomial does, right? And in fact, you would see that difference anywhere away from 0, no matter how big the polynomial is. But what we're trying to see is that difference is called the remainder. You can see the function itself. What's the difference? It's the Taylor polynomial minus this thing that we're calling the remainder. Okay, so the difference between, and then if you can even solve this for Rn here, Rn, the remainder itself is going to be the Taylor polynomial itself minus the actual function, okay? And so what do we want to see here? We would like to see that remainder be as small as possible, right? The remainder, again, is the difference between what the polynomial, the approximating polynomial outputs for any x value versus what the function itself outputs, right? So if the function itself is outputting something different than what the polynomial is outputting, there's that difference there. we would like that difference to be as small as possible. It turns out that difference actually does go to 0 as you take this limit, or at least for most of the functions, all the functions we're dealing with anyway. So we can say that note r sub n, this remainder, is going to go to 0 as n goes to infinity. So in other words, when we finally get that equality that we were talking about, when we say, here's the Taylor polynomial, the limit here, when you take that limit right there, what happens when you take that limit? Well, you get this exact value here, and what happens to that thing that we were calling the remainder? Well, the remainder itself disappears, goes away, and that's exactly what you want to see, because you don't want to have any difference between the function output and the polynomial approximation output, or in this case, it won't be an approximation, it'll be equality, right? So the point being, there is no difference. The Taylor polynomial, sorry, the Taylor series, once you take that limit as n goes to infinity, is in fact exactly the same as the function, because there is no remainder. The remainder is 0. All right, so for the purposes of this class, we can assume that that remainder is going to go to 0 every time. In the book, you might see that they'll talk about showing that that remainder does go to 0. I don't think that's even necessary. For every function we're seeing in this class, it is guaranteed to go to 0. Okay. So anyway, what we have here is a formula for the Taylor series expansion of a function. Taylor series is a special power series. What do we use Taylor series for? The Taylor series is the general formula that allows us to find the power series for any function, not just those ones that we saw in section 11.9, right? So let's see how these work then using an actual example. So again, this is kind of just a different way of finding power series for functions. We had that method that we saw in section 11.9. This is another way to do it, okay? And I'm going to, in fact, in this problem, I'm going to show you both ways, and you can kind of see how we arrive at the answer for one of them, and then we'll see that the other way that we saw in 11.9, of course, is going to produce the same answer. So notice that this is actually centered at c equals 2. That's important here. How do we do this? Well, the goal is we're going to use this, we're going to find the Taylor series for this. We're going to use this formula here. And we're centering it at 2, so we need to put a 2 there. Fn of 2 divided by n factorial. And then we're going to have x minus 2 to the n there. All right, now notice in this formula, the only thing that we really need to find, the rest of this, the only thing we really need to find is just this. That's it. Because the rest of this, that, and that, those are just part of the formula. There's nothing to find there. That's just part of the formula. So the only thing we actually have to do here is find a formula for Fn of 2. All right, that's the goal. Find a formula for the nth derivative at 2. If we can find that formula, then we just plug it into that formula for the Taylor series, and that's it. We're done. So how do we find that formula? And remember what that means. That's the nth derivative of the function evaluated at 2, okay? So in order to find that formula, what you want to do is see what the first few derivatives are, and then see if you can find a pattern for that, okay? So in order to do that, I'm going to rewrite the function like this. It's easier to differentiate like that. And I'm going to take the first few derivatives and see if some kind of pattern starts to emerge here. So this becomes negative 1 minus x to the negative 2, and then don't forget that there's a chain rule here. The derivative of the inner function is negative 1, and so this is going to become 1 over 1 minus x squared. Okay, so that's the first derivative. Let's see what the second derivative is. So notice the second derivative, I'm going to have that minus 2 is going to come down. Now, I'm kind of skipping some stuff here because look, when you take that derivative, remember that comes down, canceling that negative there, right? And then it's going to go to the negative 3. And so then here we would have that negative, but then we would also have another negative there again, right? And so those negatives cancel again. So what you'll find is that all these negatives are going to cancel from every derivative. So we're not going to have any negatives at all. Everybody see how that works? So every time the negatives cancel. And so we'll get here 2 over 1 minus x to the third. And then let's just do a couple more here to see if we can get the pattern. And so then here we're going to have 2 times 3, that's 6. 1 minus x to the fourth. Oops, negative fourth, I mean. And so that's the same as 6 over 1 minus x fourth. And I think one more is probably enough to see the pattern. Here's the fourth derivative, and so that's going to be 24, and then we'll have 24 over 1 minus x to the fifth. And so really, do we see the pattern now? So I would then say dot, dot, dot. Let's see, if we just keep going, what is the formula for the nth derivative? So here we would just check for matching stuff here. Like, for example, we're on the third derivative on that step, right? And that number right there, that is 3 factorial, right? So when I'm on the third derivative, I see 3 factorial here, and I see one higher on the power, right? That's a third derivative, but I see a fourth power there, right? Here's the fourth derivative. This is 4 factorial, but I see a fifth power right there. So I have to put all this together when I'm figuring out what that formula is. So what is the formula then? In the numerator, it seems that the derivative that I'm on matches the factorial that's showing up, right? So I should see n factorial here. In the denominator, I see that the power there is actually 1 higher than the derivative that I'm on, right? And so I should see n plus 1 for the power on that exponent there. Okay, everybody see that? Right, n plus 1, exactly. And so then next, what I'm really after here, though, is this. I really want fn of the center. So how do I find that? Well, I just plug in 2 for x. So I get n factorial over, and then I get 1 minus 2. I would have negative 1 to the power of n plus 1. Okay? And in fact, just to make things a little bit easier, that can also be written like this, right? Because if it's just alternating pluses and minuses, it doesn't matter whether you put that in the numerator or the denominator. So again, now thinking about what the formula is, right? What was the formula? It should be this, right? Fn of 2 over n factorial x minus 2 to the n. Right? That's what I had written above there, right? Same thing. What I just found here, that's what I wanted, right? And there I am. That's the step, right? And now I can just replace it with what I just found. So what am I going to get from that? I'm going to get negative 1 to the n plus 1, n factorial, and the n factorial that's already there from the formula itself. Those cancel, and we're left with simply this. Okay? Now, when we are asked to find the, now in this problem we aren't asked to do it, but if we were asked to find the interval or the radius of convergence, either of those questions, keeping in mind where this is actually coming from. This is not coming from a geometric series, right? This is just simply coming from the Taylor series formula. That means that endpoints could potentially be included, and we don't really know what the interval of convergence is. So if you were asked to find the interval of convergence, what would you have to do here? You'd have to use the ratio test, just like we were on the stuff in section 11.8. Okay, got to use the ratio test to find the interval of convergence here, and then if it asks for interval, you'd have to check the endpoint separately. Anyway, so what we've just found, keeping in mind, is the power series representation for this function 1 over 1 minus x, centered at c equals 2. Okay. Now let me show you, remember I told you that this is just a new way of finding a power series representation of a function. I've already seen a way to do this in section 11.9. So this is now, let me just show you, same problem using 11.9 techniques instead. Now what was the 11.9 technique? That was to say, okay, I start out here and I will match this to the geometric power series, right? But remember, this is being centered at 2, not at 0. So if it was centered at 0, we would just be done. We would just put it down. But it's centered at 2. And if you remember what I showed you about how to make it centered somewhere else, what do? You just replace the x with what you want it to be. You want it to be x minus 2, but of course you can't just change it, so you also have to add 2. And then you distribute that minus, or actually really, just to be 100% clear here, this is what we're trying to do. So you associate those two so we can see. Add and subtract 2 exactly. And then we get, distribute that, so you're going to get 1 minus x minus 2, and then the minus sign here has to distribute there as well, and it becomes a minus 2 as well. So we get a minus 2 here, right? And then we get 1 minus 2 is negative 1, and so we're going to have negative 1 here minus the x minus 2, and then you can factor that negative out, just make this negative the whole thing, and then you could put that negative in the numerator, or negative 1 up here, And now it's exactly the way we want it to be, right? The a is -1, so I'll just put the negative in front. And then remember that since it's a plus, it's 1 plus, I have to have that -1 to the n. And then I just replace the x with x minus 2 here, and I get x minus 2 to the n. Right, so that's that. And then notice further that that minus in front can be incorporated with the -1 to the n. And so that you can write it like this, -1 to the n plus 1, x minus 2 to the n. Okay, so that's the technique from 11.9. And look at the answer that we got right here, right? Here's the answer we got from that, section 11.9 technique. Here is the answer we got by this new technique that we just saw in 11.10. Well, of course, they have to be the same, right? If they weren't the same, then something's wrong, right? But they are clearly the same, right? Both techniques produce the same answer. But I want you to just be aware. What we're doing now is we can now find the power series representations of any function we want, as long as it is an infinitely differentiable function. And this is the way that we're doing it. The way I showed up here, where you have to take multiple derivatives, see if you can establish the pattern. Once you've established the pattern, you plug it into the formula here for the fn of 2. Right, just plug it in right there. That's where we found it. Cancel whatever we need to cancel, simplify it. There's our power series. Okay. Or alternatively, you could use the method that we saw in 11.9, where we try to match it up to a geometric power series. Let's do another example then. So now some functions, there's no way that we're going to be able to write it, as the 1 over 1 minus x or 1 over 1 plus x, like in b here. Like I wouldn't be able to use this second example here in any of the techniques for section 11.9, because there's no way that that's the thing's going to ever be written as 1 over 1 plus x or 1 over 1 minus x or anything that even looks remotely like it, right? And neither are any of its derivatives. So we're stuck with this formula here. We're stuck with the Taylor series formula. Now, in this case, we might call that the Maclaurin series, because again, it is centered at 0 in this case, but that's what we're looking for. And again, in this case, what we're trying to find is this right here. What is that? Fn of x. So in other words, what is a formula for the nth derivative? Okay, well, again, to do that, just take several derivatives and see if some kind of pattern starts to emerge. And hopefully it does. So here we just have to remember our chain rule and the fact that we have an exponential function. So we take one derivative, we just have to copy the function and multiply it by the derivative of the function upstairs. That's the -4x. Its derivative is -4. That's why we get the -4 there. Second derivative, these ones are pretty easy. I think, I'm just going to keep adding another -4, multiplying by another -4, right? So we get -4 squared. Or if you want to, you could write it like, 16, however you want to do it. In fact, that might even be better, because there you can kind of see the alternating nature of it. And the third derivative, we're going to have -4 third, and that's going to give us a -64. And that's probably enough, right? That's probably enough to see that what the pattern is, right? And so when I finally reach the nth derivative here, hopefully we can see what the pattern is. And again, to establish the pattern, just notice a couple things here, right? We're here on the third derivative. 64 is 4 to the third power, right? This is always staying the same. And then also just notice that we have this alternating thing going on here, right? The alternating part of it is telling us that we're going to have a -1 to the n, or perhaps a -1 to the n plus 1. So let's see, we'll have -1. Which terms are negative? Well, it seems like the first one is, and the third, so all the odd ones are, right? So I think a -1 to the n is going to cut it there. Then we're going to have that derivative we were on was matching the power on that 4. So we're going to have 4 to the n power. And then the rest of it is just the same. Just that stays the same every time. So there it is. That's the formula for the nth derivative at x. And then what we really want here, if you remember, what we really want is the nth derivative at the center, right? Fn of 0, because that's what's in the formula here. Oh, it should be in the formula. There should have been a 0 up here. Trying to center it at 0, remember. So what is Fn of 0? Well, that's what I get when I plug in 0 for x. And so I get -1 to the n, 4 to the n, and then if I plug in 0 there, I just get e to the 0. Well, that's just 1. And so that term just becomes 1, and that's what we're left with. So here we are. We've got a formula for the nth derivative evaluated at 0. Now I can plug it in to the formula, the Taylor series formula, and say that e to the minus 4x must be exactly equal to this power series. Negative 1 to the n, 4 to the n factorial in the bottom, x to the n. So there it is. Now for these, again, we didn't see, this didn't come from a geometric series, so there's really no way to tell what interval of convergence is going to be without doing the ratio test on this. And again, this wasn't asked for, so we don't have to do it on this problem. But if you did want to find it, you would have to do the ratio test to figure out interval of convergence. Okay, so that's that. The binomial series is just, well, there's a Taylor series for that as well, and they just give you the formula for that. That k over, that thing that you see where it says binomial series, with the parentheses, it kind of looks like a fraction, but it isn't. It's got the k and the n like that. It's not a fraction. This is actually combinatorics notation here. And the way that we say that is n choose k. And there's actually a button on your calculator that will do that for you, the combinatorics. It's basically the number of ways that you can arrange see, how does it work? If you have a set with n items and you want to figure out a way to arrange k of those items.
It's the other way.
Oh, okay. If you have a set with k items and you want to figure out the way to arrange n of them.
Yeah, right? Exactly.
Okay, cool. Let's just do that one example just so you can kind of see how it works. And I'm not even going to use the combinatorics on that one. I'm just going to... On these ones, the thing about these is that you can't even really write an actual formula. The best you can really do is just kind of write out the first several terms of it. I mean, the formula does have that combinatorics on there, but without using that, you can write out the first few terms. Okay, so for this one, basically you just need to identify what the k is and what the k is. That's really it. And so what you would do is first just write this as, so here we would just identify that this is the k, and then just use that in the formula. So we could write this as, so let's see, it's going to be 1 plus, what's the k? The k was negative 1/2, so we'll have minus 1/2 here. And then x, and then plus k minus 1. So k is 1/2, so you'd have 1/2 times negative 1/2 there over 2 factorial, which is 2. Of course, we could simplify this in a second here, but this is the idea. And then third one, 1/2, negative 1/2, negative 3/2, all multiplied. 3 factorial 6, x to the third. That's probably good enough. And then we can just say, simplifying this, we get 1 plus, or actually 1 minus 1/2 x. That one's also going to be minus. That's going to be 1/8, I guess. So minus 1/8 x squared. That one's going to be plus. So we'll get plus. What is that going to be? 8 there. 3 over 48. What is that? 16? 1 over 16. Is that right?
Yeah, that sounds good. Because the 3's are going to cancel on that.
Yeah. Okay, cool. And then x to the third. And so on and so on. Keep going like that. So again, basically what that means is that if you want to think about what this graph of this function would look like, if you were to graph that function on your calculator and look at it, and then you were to graph this polynomial function, at least several terms of it anyway, of course you would find exact match, or at least very close match, depending on how many terms that you actually graph. All right, so that's that. Oh yeah, now the final thing on this section is that that table is actually going to be pretty useful to us. And so what this table is showing, so if everybody wants to just look at that, says formulas for exam 3, last bit of 11.10. How do we make use of this table? What it is, it's the Taylor series formula that, again, the authors of this book or somebody made the Taylor series expansions for all of these basic functions, okay? So that we don't have to do that for every single basic function that we run into. And how do we use this table? Well, let's do one of these examples and I'll show you how you make use of this table. So example 3 is, again, making full use of the table. Find the Maclaurin series for the function. Use the table of power series for elementary functions on page 770. That's the same table that you're seeing copied there on the worksheet. Okay, so how do we use the table? Well, what you would look for is you go down the table and look for the power series expansion for ln x. Okay, so you'd say, here's the one for ln x. And I'm just going to write it as its power series. I'm not going to bother with the term. If you want to write it as a power series with the summation notation, you just look at that nth term, and the nth term is where it says equals, and then it's got x minus 1, minus, plus, minus, and then it's got a plus dot dot dot, and then it's got a plus, and then it's got a formula there, right? That formula is the same thing that you would put right here after the summation symbol. So this is, again, just shorthand way to write out that particular power series. Okay, so that's the one that the table gives us for ln x. Now, how are we going to use that to figure out the power series expansion for this other function up here, the one that we're asked to do on example 3? It's actually super easy. All you have to do is just say, well, this is that composition property of power series. All I do is I just see, okay, where are the x's? Here's the x, here's the x, okay? What am I going to do? Everywhere I see that x, what am I going to replace it with? That. And that's it. That's all there is to it. So really, all you got to do is just look at the power series you're given, replace the x with whatever you see in the parentheses. So I'm going to replace that with 1 plus x squared, and then we still have the minus 1 there, and then you can simplify it. Notice I am starting this at 1 because it has to start at 1. You can see why, I think. And then this just becomes x squared because those ones cancel, right? So we get x to the 2n. And that's it. Done. And notice the intervals of convergence are also given, right? Look at the interval of convergence for this one. It is from 0 to 2. Okay? That's what ln x converges. Now this one, notice that it's centered at 1, right? Because it's got x minus 1 there. However, by doing this composition and having it as 1 plus on there, we've actually moved the center, which is fine. Notice that this doesn't have that x minus 1 on there, it's just an x. So this is now centered at 0. And if it's centered at 0, that means its interval of convergence is going to change also. But notice that on this one, being centered at 1, where does it converge? 1 away, right? 1 to the left, 1 to the right. Well, the same thing is going to happen to this one. It's going to converge 1 away from the center. It's going to converge from minus 1 up to 1. And that inclusion is still going to stay there on the right endpoint. In fact, I think on this one it might actually include both. But anyway, that doesn't matter too much. All they're asking for here, I think, is just the, yeah, it just says find the Maclaurin series. It doesn't even ask for interval of convergence, so we don't care too much about that. What about sine pi x? How would we do that? Well, that one's even easier. We're trying to find the Taylor series expansion for sine pi x. Actually, Maclaurin series is going to be centered at 0. How do I do that? I go down to the table, look at the table, and again, I'm just going to use the shorthand, the summation notation for this. Sine x, again, if you look at the table, you can see after you pass the plus dot dot dot, you see the formula. It's negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And so how do I use that to find the one for sine pi x? Well, same way. Just simply replace x with pi x. Then simplify if needed. So negative 1 to the n. Replace this with pi x. And that's it. Done. Some of them you have to do a little bit more, and part C is one of them. Let me just show you how you do part C. So this one is being squared, so we can't just do the same thing because squaring it is different than just like plugging something in, composing it with something else. But it's okay because we're going to use a formula that we're familiar with, power reduction identity. So this becomes 1 plus 1/2 cosine 2x. And then if you look at the power series expansion for cosine, that's the one we're going to use. So we're going to come back to the table, look at the table and say, what's the power series expansion for cosine? So what is it? We get negative 1 to the n, x to the 2n over 2n factorial. Okay, and then using that, we can say, well, what's 1/2 plus 1/2 cosine 2x? Well, in this case, we're just going to, that 1/2 is just going to stay there. We can't really do anything with that because just leave it. So 1/2 plus, we put the 1/2 there, put the summation, and now I just need to write the power series expansion for cosine 2x. Very simple, just take the one for cosine x, replace the x with 2x. Okay, so that's it. That's all you got to do. Power series or power reduction identity. Compose the 2x with the x on the cosine power series formula. Actually, example 4 is super easy too. Let me show you that one as well. You can do the same thing if you take like a monomial and multiply it by one of those ones that's on the table. In fact, we've already done this, I think. X cosine x. Well, we just wrote down the power series expansion for cosine x. It's right here, so I don't need to write it again. So what is this? All I got to do is just multiply that by x. So x times this power series. And then we've already seen how we deal with the x like that, right? We just combine it with the other x that's showing up in the power series formula right there. So I just combine that x with this x, and that just requires adding exponents. So that's all you got to do. Okay, nice and easy, not too bad. So now these are all just examples. I don't even have any for you guys to work, so I'm just going to keep going. Now these last, or example 5 here, these ones can be a little bit tricky as well. Let me just show you how these work. Look at example 5. All right, now these ones are how do you find power series for products of two functions that maybe themselves have their own power series expansions. So like on this one, there's no way we could use, I mean, we are going to use the tables, but it's not just going to be simply a matter of composing them, like replacing the x with something else. And notice on the problem, it actually doesn't even ask us to find a formula for it. It just says find the first 4 non-zero terms. These ones are really hard to find formulas for if the formulas even exist. So the best we can do is just to write out the first several terms. And the way we do it, since they're being multiplied, is we have to actually take the power series expansion for one of them and multiply it by the other one. So I'm going to look at the power, this does take the table, I'm looking right at the table now, I'm looking at the power series expansion for e to the x. Okay, so I'm just copying it from the table, e to the x power series. In fact, I'm going to go ahead and write these as the numbers rather than the factorials. And I think 4 terms is probably going to be enough because that's all they're asking for is the first 4 terms. So that's 24 for 4 factorial, and then we just put plus dot dot dot. It is going to keep going, but we are just going to write out the first 4 or 5 terms. And then cosine x, we'll write that one too. And again, I'm just going to evaluate the factorials. X squared over 2, x to the 4th over 4 factorial, that's 24 also. Now that's probably enough terms for us to get the first 4 because you see we got a 4th power there. That's probably enough. Okay, so now what? How do we find the first 4 terms? Well, this is just a normal multiplication. Although, well, not quite normal. It's a little bit unusual in that we have infinite degree polynomial multiplied by another infinite degree polynomial. But remember how you actually have to multiply polynomials. Like if I had a trinomial times a trinomial, I have to multiply all the terms in the first trinomial by all the terms in the second one. Well, it's the same here. This is going to be every single term of the infinite degree polynomial on the left multiplied by all the terms of the infinite degree polynomial on the right. Obviously, we can't write them all down. That's why we're only going to write down the first 4. So the way that I approach this is I look at what's the lowest power product that I'm going to get out of this. Well, it's the first term times the first term, right? That's going to give me a 0 power. So that's going to give me the first term of my product, 1. And then I'm going to say, okay, well, what's the next power that I get? First power, right? Am I going to get any first power terms out of this? And I am, 1, right? The x times the 1. That's the only first power term I can possibly get. So I know my next term is going to be plus x. Now I look for second power terms. Am I going to get any second power terms? If you look at it, I am going to get more than 1, in fact, right? I'm going to get a second power term by multiplying that and that, right? And I'm going to get another second power term by multiplying that and that. Any other second power terms? I have a first power here, but I would have to have a third power there, but I don't. So there's no way that's going to happen, right? And that's it. That's the only way that I'm going to get any second powers out of this. So what we do is then say, okay, this must be, let's see, the first one I'm going to get is the x squared over 2, right? X squared over 2 times 1. The other one, I'm going to get the other x squared over 2, but it's negative. So minus x squared over 2 times 1 also. But look what happens to that. That makes that term 0, right? Oops, I don't need to have that other x squared. Sorry about that. That means that that term is going to be 0. But it says that we need to find the first 4 non-zero terms, right? And so, unfortunately, that one does equal 0, so we're going to have to not count it. So we'll have to move on to our next power, third power, right? How am I going to get any third power terms out of this? Let's see, I've got a third power here times the 1. That's going to give me 1, right? So I'll put it x to the third over 6. Any other third powers that I can get out of this thing? Looks like I got a second power times a first power, right? That produces a third power also, right? So we're going to have to include that one. We'll get minus x cubed over 2. And I believe that's all the third power terms that we can get. And remember, they're asking for the first 4 non-zero terms. We already said that that one actually is 0. So we have 3. We need one more term. Fourth powers. Where are we going to get these fourth powers? Let's see. We have a fourth power here times a constant, right? So that's x to the fourth over 24. We have another fourth power here, that times that constant. So another one of those. And we also have one more fourth power term, right? That second power times that second power. That's going to be minus x to the fourth over 4. And that's it. And then this is going to keep going. And then we just try to combine our like terms. So we have 1 plus x plus, what is that? That's going to be minus, isn't it? What is it?
I think it's minus 1/3.
X cubed, right? And the second power term was, and then that last one, was that going to be, I'm not going to think about it, 1 over 24 plus 1 over 24, or 2 over 24, I guess, minus 1/4, minus 1/6. So minus 1/6 x to the fourth. And then after that, we've found our first 4 terms, so that's it. That's all they asked for. So that, then, if you were to graph your e to the x cosine x function, just graph that on your calculator, graph this 4th degree polynomial, since it is only 4th degree, at least all we could graph of it anyway, you would see that they do match pretty closely, at least right around 0. But the further away you get, the worse the match would be. All right, so everybody see how that one works? That other one, part B, you can actually do that one in 2 different ways, and the choice is yours. But I'm going to show you one way because we just did one already. It's just like it. Okay, so we could actually do this by division, or you could do it by multiplication. Multiplying this by, and if you're going to do it by multiplication, what you would do is just what we exactly what we just did. But if you notice, 1 over 1 plus x is actually one of the ones that we have a power series for. So you could write the power series for e to the x, and then you could write the one for 1 over 1 plus x, and then you could do the whole, multiplication just like we just did. Or you can do this by division, and that's what I'm going to show you now. By division, what do you do? So you have to do long division on this one. And what we're doing is dividing that into that, right? 1 over 1 plus x into e to the x. So to do that, you look at the power series expansion for e to the x. I'm going to go ahead and write it. And that's probably enough terms for this, and we'll just keep going. And then long division means I'm dividing something into that. What am I dividing into it? Another polynomial, it turns out, 1 plus x. And so just write it out there, and then just think about how the long division works. We ask how many times does that go into that once. And so I'll just put the 1 up here. And then I just multiply that, and I get 1 plus x. And then remember what you have to do to subtract that, right? This is long division. And then I have to, so I subtract that, and then I drop down this thing here. And then really I just have to ask how many times does 1 go into that. And so for this problem, it's just 1/2 x squared, so plus 1/2 x squared. And then I think I have to drop this down too, that third power there. And then I multiply the 1/2 x squared, right? Take this, multiply it by both of those, put the result down here, subtract. This is long division. It's a bit of a weird long division, but I think you guys can see what's going on here. So I multiply that by the 1, I get the 1/2 x squared. I multiply it by the x, I get 1/2 x to the third. But then I have to subtract these, so minus, and that becomes minus also. And then you see the x squared terms cancel, but these don't. So what am I left with there? 1/6 minus, this is negative 1/3, right? So negative 1/3 x to the third. Then I drop down that 1/24. And then I ask how many times does the 1 there, go into this term here, minus 1/3 x to the third. Multiply again, so I get plus 1/3, or I get minus 1/3 x to the third. Multiplied by the x, I'm going to have minus 1 third x to the fourth. Subtract them, changes both signs here. 1/24 plus 1/3, what is that? 3/8. That's going to be 3/8 there. And that's good enough because now I just ask how many times does 1 go in there, so I get plus 3/8 x to the fourth. And that's 4 terms. So those, again, you don't have to do this long division if you don't, for this problem anyway, you don't have to do it if you don't want to. You could have done it exactly like we did the previous one, part A. Take the power series expansion for e to the x, multiply it by the power series expansion for 1 over 1 plus x. Number 6, and this is, by the way, the last problem of the entire semester. So, okay, so how do I do this? Well, look at the power series expansion for sine x. This is using the table. Right, sine x. Go back to the table. Remember what that is, or you don't even have to remember, you just look at it, write it out. Negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Take this, you use the composition property that we've been doing. Say, okay, well, what's the sine of x squared then? So just replace the x with x squared. Get x squared here instead. Everything else stays the same. And then, what's x squared sine x squared? Well, that's just what you get when you multiply that power series we just got by x squared. And again, that's not very difficult if you know what you're doing. Let's simplify that to be x to the power of 4n plus 2 over 2n plus 1 factorial. Combine that with the x squared, we get negative 1 to the n. Adding those exponents, 4n plus 4 power, all this stays the same. And then finally, integrate that, right? Because now we've got the x squared sine x squared, now we just integrate that. And so how do I do that? Well, I just integrate this power series that I just got. So rather than writing it again and trying to save time here, I just have to integrate that power series. So I'm going to get negative 1 to the n, x to the 4n plus 5, remember we got to raise it by 1, also divide by the same thing that you just raised the power to. So I also have to have that 4n plus 5 down here. And then that's it, done.